We introduce the binomial and geometric random variables. Alright, when we talked about the binomial distribution, we defined it, the variable had to meet these requirements. So it was this bins. It had to be binary, so each outcome was a success or failure. It had to be independent, so the trials must be independent, so knowing the result of one trial must not have any effect on the result of another trial. The number of trials was fixed in advance. We had a fixed number of trials, and then the success in each trial, the probability of success must remain the same. So if we were talking about tossing a coin, we have a success or a failure, so heads or tails. They're independent because knowing the outcome of one toss doesn't change the probability of another toss. The probability of success is 0.5, and if we were, maybe we said we were going to do it 10 times, so then we'd have a fixed number of trials. We can also, if we have a binomial random variable, and then if we list the values of the variable and we list the probabilities, then we have created the binomial distribution. Alright, so what we're going to talk about, this is kind of the derivation here of the formula. I'm not really going to get into that. You can pause the video if you want and read over this page. I'm just going to go straight into the example. This is just a continuation. This is the actual formula. Again, we didn't use the formula that much. If you want to pause the video and read the screen, go for it. Otherwise, I'm just going to move on. Alright, here's another slide just of the formula. Okay, this is an example here. So now in this one here we have a particular pair of parents that has a probability of 0.25 of having blood type O, so each child. Suppose the parents have 5 children, so I have a fixed number of trials. They're either going to have type O or not have type O. We're saying the probability of success is the same for each trial, and we're saying that the independence is applicable here as well. So what happens with the first trial doesn't influence the second child. So if you wanted to find the probability of exactly 3 children, you could go through and use the actual formula there and find the answer that way. What I showed you how to do was to use the calculator. So if you're going to use the calculator, which is perfectly fine, this is what you should do. So in this case, I'm going to always state what your n and your p is. So my n is 5. There was 5 children. The probability of inheriting type O was 0.25. So make sure you state your n and your p. The probability of getting exactly 3. So the probability that x is equal to 3. When we were doing exactly, we were using the binom PDF command. So it was binom PDF. It was n, comma p, comma whatever number you were looking for. Then I'd get my answer, and then I would just write a summary statement here of if I was taking the AP exam. The next question says, should the parents be surprised if more than 3 of their children inherit type O? So you're trying to find the probability that x is greater than 3, so this is how they've answered it using the formula. Again, I showed you how to do it on your calculator. So I would do this one the same way. I'd have n equal to 5, p equal to 0.25. I'd state the probability of what I'm finding, so the probability x is greater than 3. And then if you remember here, we had to do 1 minus the binom CDF. And I don't want to include 3 here. I'm jumping up to 4. So I have to subtract out everything up to 3. That's the answer I get. And so then I would also write a summary statement down there as well. If you remember those calculator commands, if you have a binomial distribution, this is a notation for the binomial. So you have a capital B there, parenthesis the n, comma the p. So you can also write like that. You can say binomial. I could say 5, comma 0.25, and they would know what you meant. Or you could just write n equals 5, p equals 0.25. Just remember the difference between the two commands. If you're trying to find exactly or equal to, that's when you use the PDF. If you're trying to find less than or equal to, that's when you use the CDF. And so then we had variations of this based on what we were trying to find. We also talked about finding the mean and standard deviation. This example right here is kind of going back through the old formula just to prove a point that there is a shortcut here. the actual formulas, and these are on the AP formula sheet. So the mean of x, so the mean, and x is the random variable that follows the binomial distribution, is just n times p. The standard deviation of x is the square root of n times p times 1 minus p. Remember, the mean is always what you expect to have happen. And again, these only work for the binomial. So the mean is 1.25, so they expect 1.25 of the children to have, out of 5, to have type O. With the standard deviation of whatever the standard deviation was with that one, that's how much the values would vary. If we look at this next example here, there he was just studying to see if his class can tell tap water from bottled water. So each has a 1/3 chance of correctly identifying. X is the number of students who correctly identified. So we'd expect about 7 of them to guess correctly because they just did n times p. And then we would expect them to differ from 7 by an average of 2.16. That's just your standard deviation. One thing that we talked about here in class, I used like a example with cereal boxes and Danica Patrick, like trading cards. One thing that we talked about here is that in reality, like it says here, suppose 10% of CDs have a defective copy protection scheme that can harm computers. And we inspect a simple random sample of 10 CDs from a shipment of 10,000. It's really not quite a binomial setting because the reality of it is that we have a finite population here. Every time we take out a CD that's not defective, we have one less. But when we multiply all those probabilities, so getting 0 defectives out of 10, we find that this is the answer. But if we were used the binomial formula, and again we could have used binom PDF, we find that this is the answer, and they're really not that different. So this is when we introduced that 10% rule. So if you're taking a sample of size n from a population of size capital N, we said it was okay, so we said that this difference was going to be minimal. So even though we were sampling from a finite population and technically our probability should be changing, we said that that difference would be okay, or the impact would be minimal as long as the sample was less than 1/10 of the population. Another thing we introduced in this chapter is what happens to the binomial distribution if we looked at a histogram of it for different values of n and p. And one thing that we noticed was that at a certain point the curve kind of became normal. And the condition for that was when n times p was greater than or equal to 10. That was like the magic number. And n times 1 minus p was greater than or equal to 10. And that was another condition that we used as we went forward. We also talked about using the normal distribution to approximate a binomial. On the AP exam, you can obviously answer any question with the binomial distribution. You could replace it with the normal approximation if that rule of thumb is met. Remember, you'd find your new mean and your standard deviation. That's what you would apply when you did your normal CDF. I don't think they'll ask you to do the normal approximation for the binomial, though. Alright, the next thing we called was the geometric. So the geometric had different conditions. The big thing that changed here was that we didn't have a fixed number of trials. We were trying to look for the trial in which we had our first success. So these problems were phrased a little bit differently. They still had a success or failure. They still had to be independent, and the probability of success remained the same, but we didn't have a fixed number of trials anymore. You can read over this if you want to. Alright, they have here, you're trying to guess, how many guesses does it take until you get you correctly identify the birthday of one of your teacher's friends. So what's the probability the first student guessed correctly? What's the second, the third? And they're talking about the birthday, so Sunday through Saturday. So there's only the probability of that being successful is 1/7. I'm just going to look at this one right here. So the probability of it being y, so that would mean the first student was wrong, the second student guessed wrong, and then the last student guessed correctly. That was that probability right there. So when I showed you how to do it on the calculator, we use the geometric distribution. So remember that geometric, it's just, there's only one parameter in that. It's just the probability of success. You can have the exactly one again, where you have the PDF p comma k, or you can have the less than or equal to with the CDF p comma k. For that example right there, if I wanted to find the probability that I was exactly 3, so it took the third student, and the third student guessed correctly, it's 1 over 7 comma 3 equals, that's the answer. So I got the same answer as I got here. I didn't really write a very good summary though. I probably should have said the summary, the probability that the third student guesses correctly is 0.105, because that's what it really is. What I wrote there is wrong. So there's a pattern there. This was the formula, but again, you can use those calculator shortcuts. The mean of the geometric was just 1 over p, and again, they might say on which trial do you expect to get your first success, and then you could just find the mean. And that was pretty much it for this chapter.